We're solving problem 10 from the 2021 AMC 12A. Two right circular cones with vertices facing down as shown in the figure below contain the same amount of liquid. The radii of the tops of the liquid surfaces are 3 centimeters and 6 centimeters. Into each cone is dropped a spherical marble of radius 1 centimeters, which sinks to the bottom and is completely submerged without spilling any liquid. What is the ratio of the rise of the liquid level in the narrow cone to the rise of the liquid level in the wide cone? So we have these two crudely drawn cones because I don't have special tools to draw them. But these are the two depicted water levels. They are not drawn to scale, but just imagine they are. We can quickly create a chart for the areas and all the variables of the wide and narrow cones. So let's go with narrow at the top and wide at the bottom. Here is the radius, or radii, because we're talking more than one, and it's the radii at the tops of the waters because it helps us find the total area of the water. So we have the radius, height, and area, or volume. So we have that. Now the radii for the narrow is 3 centimeters and for the wide is 6 centimeters. The height for the narrow one, let's just call that one h1. And respectively, the height for the wide is h2. And therefore, the volume of the narrow one is 1/3 pi h1 3 squared, or just 3 pi h1. Similarly, this is 12 pi h2 because 6 squared is 36, and the additional 3 from 36 cancels out with the 1/3 from the original area of a cone. Since we know that these volumes are equal, we say that 3 pi h1, I keep on writing hi, h1 is equal to 12 pi h2. So the pi's cancel out, and this becomes a 4, and the ratio of the narrow cone's height to the wider cone's height is, well, that's just 4, h1 over h2. Remember, this is before the marble drops, because we aren't considering the increase in height. So once we do consider that, we can rewrite or remake the table again. And this time, we want to make it show the increase in the height. So this time, it's going to be a bit different because, so we're still going with the radii here. I'll just write radii, RAD period. Well, now for this one, it's not 3, it's 3x because there's an increase. Similarly, the wide is 6y, since we're dealing with different variables and different lengths. So height increase for the narrow is h1 x, and this second one is h2y height. So the volume, well, that's for this one, it's still going to be 3. Still going to have a pi h1, but you have to add another variable, the x in this case, because that shows the increase in height and volume. So this is x cubed because you're multiplying it 3 times, as you have to square it by the radius and then multiply it again in the height. So therefore, the volume of the wide cone after you drop the marble in is 12 pi h2 y cubed. And since we know these are equal because the problem states that the volumes of water are equal and you drop the same marble in, 3 pi h1 x cubed is equal to 12 pi h2 y cubed, And as you know, we know the radius, or we know the ratio of this, so all of this just cancels out to get x cubed is equal to y cubed, therefore x equals y. So now the change is, the value we want is the change in height for the narrow, h1 of x, and then you subtract h1, so you can factor out a h1, and then this is x minus 1. Same thing down here, h2 y minus 1. And since we already have stated or shown here that the variables x and y are equal, whatever the ratio of x minus 1 to y minus 1 are, that's still going to be equal. So what we want to find is h1 over h2, or 4, or as the problem wants it, it has a ratio of 4 to 1. And that is our answer for this problem.